Cool, so welcome everybody to JavaDay, and today I'll be sharing with you some cool stuff on garbage collection. I'm gonna be sharing with you some of the algorithm that's being used on behind the curtain of your Java application, and I'm gonna be using OpenJ9 as a real-world example for that. My name is Igor, and I'm really excited to share all these with you. So let's get started. These are just important disclaimers saying that these slides are just for information purposes. So the outline of what I'm going to be going through today is the main part of the talk is going to be on garbage collection algorithms and how that's being used by your Java application. Then I'll be sharing the last part of the talk is going to be on double map arraylets, which is an advanced feature that we use to optimize storage of large arrays in region-based GCs. I completed my master's in model and compilers, machine learning, artificial intelligence, bioinformatics. I'm really also really like that topic, and I'm a tennis addict. So with no further ado, let's get started. If you want to get the binaries from both Hotspot and OpenJ9, which are both the most common used JVMs out there, you can get it from Adopt OpenJDK. So that's the link. You can get those if you want to play around with them. I would highly encourage for you to try out all of them and different GC policies to see which one best fits your application, because you'll be seeing that there's no perfect GC that fits every application. And with this knowledge that I'm going to be sharing with you today, I hope to share this knowledge, and with that, you're going to be more capable of choosing the best garbage collection policy and tune that for your application. So OpenJ9 is a fairly mature project. It came to the open very recently, actually in 2017. And a fun fact about OpenJ9 is that it started as an embedded JVM. If you guys are familiar with it, when it comes to memory management, OpenJ9 is great. Now, garbage collection. So what is it? This is a more by-the-book definition. Garbage collection is a form of automatic memory management. The garbage collector attempts to reclaim memory occupied by objects that are no longer in use by the application. That's in contrast to other programming languages like C++, right, where the programmer has to manually allocate and deallocate memory using, say, malloc and new, and to deallocate free and delete, right? So what are the responsibilities of garbage collection? So garbage collection reclaims, allocates memory, right? It's responsible for allocating objects in the heap. It identifies the liveness of data, and all that data that's not considered live, it's by definition considered dead, therefore garbage, which can be reclaimed by the garbage collection. Some positives of garbage collection here. It's an automatic memory management, right? So it lifts the burden of every time automatic for you, which is the case of Java, right? And helps reduce the categories of bugs, for instance, dangling pointers, double freeze. So it's great. But on the other hand, we have some negatives, right? It requires additional resources, for instance, more CPU cycles, more memory. It can cause unpredictable pauses, which are known as stop-the-world pauses, where all your application threads are stopped so that GC can collect the garbage. It may introduce runtime costs, and application has a little control of when memory is reclaimed. You can kind of control, you can call system.gc, which is going to trigger global GC, but that's only a hint to the GC to trigger garbage. Cool. So there are many GC algorithms out there, and I'm going to point you to the GC Bible, which is a book where you can find all this information. But throughout this talk, I'm going to be talking about the different policies, and each of them is going to be used some kind of these algorithms. One that I'm not going to be talking about is reference counting, but reference counting is really simple, where in reference counting, each object, which I'm an object, and there are two objects that have two references, each have one reference to myself. So my count's going to be 2 because I have 2 references coming to me. So once that reference reaches 0, then I'm considered garbage, therefore I can be reclaimed. So that's reference count in 30 seconds. And the other ones are going to be explaining throughout the talk. All right, so I'm going to be going over a few different policies, GC configurations. So the first one's op throughput is a stop the world parallel collector. Then I'm going to talk about GenCon, a generational copying collector. Then GenCon CS is a pauseless collector. Metronome, increment soft real-time collector. And lastly, balance region-based collector, which is really similar to G1 from Hotspot, if you're familiar with that. So op throughput. So op throughut is a parallel global collector. Parallel means that multiple GC threads are going to be collecting garbage. Its operations done in stop the world, meaning all the application threads or potato threads are all stopped and GC is doing its work. It does its work in a mark, sweep, and option compaction collector. And like I said, all GC operations are in parallel. And there's some extra native memory overhead because it metadata. So whenever we have GC or your Java application, we allocate objects on what we call the heap, which is normally, not all the time, normally is a contiguous block of memory, and that's where you're going to be allocating objects. So op throughput has a flat heap, a contiguous block of memory in this case, and we further divide this heap into 2 logical areas, small object area and large object area, where most of the objects are located in the small object area. If an object surpasses a certain threshold, we put in the large object area. So this is how an application under this policy behaves. So the white arrows, they represent the application thread, and the red arrows represent the GC threads. So application threads starts whenever we deplete the heap, whenever we hit an allocation failure, we stop all the application threads and we trigger a GC. So that's the red arrows there. Once the GC is done, then application can continue from there. Then whenever we hit an allocation failure again, we hit another GC cycle is completed, then and so on. And this GC cycle, no application. Now, each GC here is divided into 3 phases, right? Marking. So marking is where we find all the live objects through the object graph, through the roots. Then once we mark all the live objects, we sweep, meaning we reclaim memory from all these dead objects, or all the objects that's not considered live. So I was talking about compaction, because after a few GC operations, after a few GC cycles, your heap can get fragmented, like a Swiss cheese. So what's heap fragmentation? That's how your heap is going to look like after some little time their application is running, after a little bit of GC cycles. And it's going to become like a Swiss cheese, a lot of little free spaces. You might not have enough contiguous space to allocate an object. So what to do in that case? We do a compaction, right? So you take all these live objects, put into one side of the heap, and then we can continue the application from there. All right, so that's op throughput. Now let's talk about GenCon. GenCon, if you're familiar with CMS from Hotspot, that's really closely related. They both have new old space and they both use generational. Generation meaning each object's here now going to have ages. If an object survives a GC cycle, its age is incremented. It provides a significant reduction in GC stop-the-road pause times. We need a write barrier here because now we're going to be marking objects concurrently with the application, which wasn't the case from op throughput. And we have a concurrent global marking phase, which is the concurrent marking phase here. So instead of dividing the heap into a small object area and a large object area, we divide the heap into new space, which is nursery, and old space, which is tenure. We further divide nursery into 2 logical spaces, allocate and survivor. So all objects are put into allocate space, and we then, whenever that allocate space is depleted, we copy the objects to the survivor space. So GenCon uses what we call a copy collector, where that all the live object gets copied to the survivor space in a stop the world manner. So that's how our application behaves in this case. So again, white arrows represent an application thread, and red arrows represent the GC threads. So scavenge here is the copy collector. And like I said, this copy collector is going to be copying objects from allocate to survivor. So when we hit the limit of allocate space, we trigger scavenger, the copy collector, and then the application can continue after that. But after some time, you're going to hit a point where global marking phase is going to start. And the global marking phase is there to mark the tenure concurrently with application, because scavenger is only collecting objects in the new space. And the old space we don't collect as often because some objects live a long life, so we don't need to do that as often. So global marking phase collects only marks those objects in tenure space concurrently. And we can have scavenger running at the same time as the global marking phase, because that's only dealing with the new space while global is dealing with the old space. And at the end of the global marking phase, we sweep the old space with the sweep phase similar to the up throughput. So we collect the garbage from the tenure space that way. And here, since global marking phases marking objects concurrently, we need these barriers, right? So whenever we set a field, a reference for an object like that, we need something to remember that, because let's take the following object graph, for example. So imagine the case where GC is marking objects while application thread is running concurrently. So GC has already visited the root, has already visited object A, is in the middle of traversing object B, and hasn't seen the object C yet. So in this case, application thread comes along and deletes the pointer from B to C and adds a pointer from A to C. And then the GC comes along and says, okay, I'm done with B, so I'm going to mark B as processed, right? And this is my resulting object graph where C hasn't been marked because application thread came along and modified its pointer somehow. And we're going to collect C erroneously here, and that's not good. So because of that, we need a right barrier here. So what can we do? So the barrier is implemented this way. So after the store here, we check, is there concurrent GC active? Is there a concurrent marking phase active? If it is, we dirty that object, in this case A, so that at the end of the GC, we go to this card table and traverse these objects that we might have forgotten if we didn't have the barrier. And so in our case, we would remember object C instead of collecting it erroneously. But we do have another barrier in this case, because remember, here we have two spaces, the new space and the old space. And we might have objects in the old space that reference objects in the new space. And we need a way to remember that as well. So we have a simple check, right? We check if object A is tenured, and if object A is in the old space and object C is in the new space, right? We also need to remember A. And since here we have two barriers, we can just put that in the same barrier. So we have the inter-region barrier there and the concurrent marking phase barrier there as well. Cool. Now let's go for a third concurrent scavenger, or third policy, sorry. That's an improvement upon GenCon. And it's also a generation copy collector. This is a pauseless GC where the focus of this GC is to decrease the GC pause times as much as we can. And if you're familiar with other pauseless GCs like Shenandoah or ZGC, it's not the objective is the same, but underneath the layout and everything is a little bit different. And here we're going to be copying objects concurrently. So the biggest difference between concurrent scavenger and the regular scavenger that I just talked about is that scavenger here, instead of being stop the world, it's going to be running concurrently with the application. So we're going to be moving objects along with the application. So here the heap is divided similarly with GenCon, new space, old space. And the biggest difference here is going to be this. The CS there stands for concurrent scavenger. So remember before, scavenger before was just one stop the world phase. Here it's running concurrently with the application. We have two little stop the world pauses there, one at the beginning and one at the end. The one at the beginning is so that we can traverse the routes, find all the routes on the object graph. Once we have that, we can continue, we can let the application run along with the GC threads, which you see the yellow arrows there. Once we're done with the collection, then we have a final little stop the world pause there to bring all the GC threads into synchronization, and we're done. So that's the main difference here. We are running our copy collector concurrently with the application. And the global marking phase here is still the same. Nothing changed there. Cool. So here we have an issue because we're moving objects with along with the application, right? So the mutator is also trying to access these objects while the GC is moving them. So how is that done? Okay, so let's step back a little bit, right? So let's think about our parallel scavenger here, where we're going to have multiple GC threads running, no application threads, right? So how is that done, right? So what the GC thread is doing in this case here is just trying to copy an object from one place to the next. So we can get away with an atomic operation, a CAS in this case, compare and swap. So in this case here, we have two GC threads, which is trying to copy this object from the from space to the to space here. So what happens here, they run with this atomic operation to copy the object. So in this case, the brownish GC thread wins to install the forward pointer. So that thread copies the object. The other thread, the green thread, GC thread here, so I lost the race, but that's okay because all I want is to copy as many objects as I can. So I'm just going to continue to do my work here and copy some other object which is in my work queue, right? Now, so what happens whenever we have a GC thread and a mutated thread running concurrently with the application, right? So this is different, right? One GC thread and one application thread running. So let's imagine we have the same CAS operation here, which is try to install the forward pointer here. So let's see what happens. So in this case, let's say the GC thread won the race. The mutated thread is going to be, okay, I lost the race, but I can see there's a forwarding pointer, so I'm going to follow that and access my object. But since GC thread's in the middle of copying the object, that if it's not fast enough, that can be a problem, right? So we need to be a little bit cleverer here in order to solve this situation. So what do we do? So in this case, we unconditionally copy the object. So both GC thread and mutated thread is going to copy the object, and then they're going to race to install the forwarding pointer, right? So how does this work? So both of them is going to copy the object, right, unconditionally. And then at this point, they're going to race to install the forwarding pointer. So let's say GC thread 1 here, right? So now the actual copy that we want to use is the one that the GC thread 1, right? So mutated is going to be, okay, I lost the race, but I can see the forwarding pointer here, and since GC thread already copied the object, I can access the object without any trouble. So here, this is what we call read barrier, and if you're familiar with Shenandoah version 2, they use a similar barrier to deal with this racing between GC threads and mutated threads. Cool. Now Metronome, it's our fourth policy here. It's an incremental soft real-time collector. It tries to put an upper bound on GC pulse times. What that means is on a window of 10 milliseconds, we're gonna give 70% of that time to the application and 30% to the GC. So during those 30%, GC can do some work or give it back to the application. So we guarantee that 70% is going to be dedicated to the application. We use a different barrier here called Snapshot at the beginning barrier. And because of this barrier, we have a high percentage of floating garbage, and you're going to see why that's the case. So here, instead of the heap being divided into new and old space, the heap is divided into regions. So here, regions are 64 kilobytes, and the bigger the heap, the more regions we're going to have. Here, regions are assigned a cell size, meaning objects of the same size is going to be on the same regions, which is a very good advantage of this policy here. Objects that are larger than 2 kilobytes might span multiple regions, right? With the exception of arrays. So if an array is larger than a region here, we're gonna divide this array into chunks and put these chunks into different regions. And in the header, we're gonna have pointers pointed to this array. And this is what we call arraylets. I'm gonna be explaining a little bit more what arraylets in future slides. So how Metronome works? Metronome is really simple, right? So there, again, white arrows are the application threads, red arrows are GC threads. So remember our up-throughput policy, which is our simplest policy, which is that huge top-of-the-road pause time, right, whenever we deplete the heap. So imagine that huge top-of-the-road divided into small increments. That's pretty much what Metronome does, right? It does a little bit of work at the beginning, then let the application run, does a little bit more work, let application run, a little bit more work. So do small increments of GC work so that application can have that 70% chunk on that 10 milliseconds window. So Metronome has this barrier called Snapshot at the beginning barrier. It causes a lot of floating garbage, and the barrier has to be performed before the store. So here I have an example to show you why this causes a lot of floating garbage. So remember, we have the following object graph. And we are in the middle of marking objects, right? GC already traversed the roots, already traversed object A, is in the middle of processing object B, and hasn't visited object C, neither object D. An application thread comes along and adds a pointer from A to D. So far, so good. And another application thread comes along and deletes the pointer from B to C, right? And now that we no longer have that point from B to C, GC thread is going to be okay. I'm done with B. I'm going to mark B as completed, and then I'm going to collect C and D because those are not marked, right? So we use Snapshot at the beginning here, and Snapshot here, instead of being triggered on object write, it's triggered whenever we delete and reference from one object to the next. So here, the Snapshot at the beginning barrier is triggered whenever we delete this reference from B to C. That's when we trigger our barrier. And instead of having something like this, with the barrier, we would end up with this object graph. And you can see with this object graph here, is that we would remember both object C and D, even though we don't need C anymore, because that just happens to be in the way of object D. We're going to remember that because of how the barrier works here. And in this case, C is considered floating garbage. So this is how this barrier is implemented, right? So we store the field in a temporary variable. So we check if the barrier is active. If it is, we remember that temporary active, which pretty much means we're going to remember that reference from B to C. That way, we can remember all those references that if we didn't have the barrier, we would erroneously allocate those objects. Cool. Lastly but not least, we have our balanced policy. Let me check how we're doing time here. Okay, we're still good. So balanced is a region-based generational collector, similar to Metronome, but in this case here, we have, instead of the region, we have this objects of the same size. Each region is going to have an age. And if you're familiar with G1 from Hotspot, they are very similar, right? They're both region-based, they're both generational. One difference that I can see it right now is that G1 has I believe it's 3 different ages. We have 24. And that's, I think, one of the main differences we have, but they're really close related to each other. They provide significant reduction in the max GC stop-the-world pause times. Introduce a write barrier, because remember, we're going to have different regions. And this region can have references coming from other regions to this region here. So we need a way to remember that, similar to the GenCon barrier, where we have to remember objects from old region to the new region. And this have a really cool feature with incremental heap defragmentation, which I'm going to show you with a cool graph in a little bit. So like I said, heaps divided into regions. But here, the bigger the heap, the larger the region, because we try to have around 1,000, 2,000 regions at most on this policy. We object allocate in what we call add-in regions, which are new regions. And if an object is larger than a region, we just throw an out-of-memory error, with the exceptions of arrays. And we have a similar technology here, Arraylets, where we chunk this array into different parts. And if an array is bigger than a region, we put a part of the array here, another part of the array here, and have references to those parts in the Arraylet header. Cool. So this is how balanced GC behaves. White arrows again, application threads. Red arrows are the GC threads. So PGC here stands for partial garbage collection. And this is a copy collector, kind of similar to the scavenger, right? Where PGC is going to look for those regions with the most return of investment. So think of, say I have a region that only has one live object. That's a really good region for the PGC, because all it has to do is get this live object, copy it over to another region, and there you go. We have one region, a full free region to work on, right? So PGC tries to find those regions where it's going to collect those regions with the least amount of work and have that region free. It's a stop-the-world copy collector. So we might have multiple PGCs along the way, right? But one thing here is that this copy collector only has local information about the regions. So with time, it's going to lose this information. But that's okay, because we have GMP to the rescue here. So GMP stands for Global Marking Phase, and its sole job is to mark objects, right, and help PGC with this local information, because GMP has this global knowledge, and at the end of the GMP is going to update PGC information so that it can make better decisions on what regions to collect. okay? So what the global marking phase is doing, like I said, this does not reclaim memory, right? Only perform marking phase. It's scheduled to run between PGCs. It builds an accurate mark map for the whole heap. And this is what is going to be used to update PGC's information whenever the GMP is done. So this is what happens. So this graph represents the lifetime of application running with balanced policy. So on the x-axis, we have time. On the y-axis, we have free heap. So the lines going up is the garbage collection doing work, the PGC collecting garbage. Lines going down is the application collecting, this application consuming memory, right? So you can see in the beginning here until time 170 that if that trend continues, we might hit an out of memory error, right? That line, that trend going down is because PGC is losing this local information. So GMP is clever enough to trigger at that point so that it finishes in a timely manner to update PGC. So once PGC information is updated, PGC now starts to defragment the heap because it has the most updated information about all the regions. So you see now this trend going up, which is PGC is defragmenting the heap. But then after a while, that trend starts again where we fragment the heap and then we have to trigger another global marking phase. And then we have this trend of balanced. Here we need a write barrier, right? Like, why do we need a write barrier here? Very similar to GenCon, we can have references to these objects coming from other regions. But differently than GenCon, multiple regions can point to this object here, right? So we need to keep track of that somehow. And the way we did that is through the write barrier. And here we do a slightly different than the write barrier from GenCon. So here we unconditionally dirty every object, right? And at the beginning of the PGC, we go through those dirty cards and check for inter-region references. So whenever we develop a read or write barriers, it's always a trade-off, right? Do we want to put the burden on the mutated thread, application thread, or do we want to put the burden on the GC thread? Here we chose to put the burden on the GC thread so that the application thread don't have to worry about checking if there's an inter-region reference, right? All it has to do is just dirty that card, then PGC is going to deal with it. It's going to deal with it later. Cool. Now, arraylets. I mentioned very briefly what arraylets are, right? So arraylets is a clever way for us to store a large array in region-based GCs. So what we do is we take this large array, divide into chunks, right? And these different chunks go into different regions of this region-based GC. And in the arraylet header, we have references to these regions. So this is a picture that shows that. So in the bottom, we have the header, right? And the arrayoids are the pointers to the arraylet data. So imagine we want to access the first element of this array. So what we would do is we would follow the first arrayoid, which is the first reference there. So we'd go to that last blue region there and access that element in there. So that's how we store this large arrays into region-based GC. Because if we didn't have this, we would have to put this contiguous array that spans multiple regions, right? But there's a problem. There is some APIs that require contiguous view of an array. And that's the case of JN9 Java native interface, critical APIs. So these APIs, we cannot just pass the pointer of this array because it's not contiguous, right? This chunks is everywhere. So what we do now to mitigate that? So what we do is, what we used to do is we copy the arraylets into a temporary array, which is contiguous, right? And then we pass that address to the API, to this Gen9 API. The client does whatever it has to do with the array, right? Can modify some objects. And then we have to copy everything back to the original array. And as you can imagine, this is very expensive. So double mapping to the rescue. So we leverage the virtual memory in 64-bit systems, which is very large, to the 64 in fact. And we think about that because physical memory is fairly limited when compared to virtual memory, right? So what we do here, we take two virtual addresses and map to the same physical address. And if you're familiar with ZGC, it uses multi-mapping, this same technique. And it uses multi-mapping to keep track of where the object is in which GC cycle, right? So this ZGC uses for every object. Here we only use for large arrays. So here, like I said, we map two virtual addresses to the same physical memory. And the nice thing about this is that any modification to any of these virtual addresses is going to be reflected in the other virtual address, which is really cool, right? So how does, if I could picture this, this is how the double mapping would look, right? So in the bottom there, we have the different chunks of the array, and then we map that to a second virtual address to make it look contiguous. And for those APIs that require contiguous representation of the array, all we have to do is pass the address of this second virtual memory, which has our contiguous array. And every modification there that we do there is reflected in the original array, which is really cool. And with that, we boosted array operations like 30 times. So that's quite good because we don't have to copy element by element to a temporary array anymore. Cool, so what's next? So double mapping is only available on Linux. So how can we do better? So currently we are working on something that we call off-heap. And what is off-heap? Off-heap is a secondary heap that we're going to be storing large objects in this off-heap, right? So that's being currently done right now under development. So stay tuned for that. Hopefully I can share with everybody soon. So this is a quick guide on the different policies, how I'm doing on time. Okay, still have a few minutes. I want to leave for some questions at the end. So these different policies, for instance, some of them are generational, like GenCon, balance, right? Most of them have some type of concurrency in them, right? Most of them mark objects concurrently, but only one of them, GenCon CS, moves object concurrently. And they have different heap layout, right? Balance and Metronome are region-based, while GenCon has new space, old space. And Throughput has a small object area and large object area. But which GC is best for your application? So this is more like a general tip, right? GenCon and GenCon CS are good for web servers, desktop applications. Balance is very good for very large heaps. Metronome is good for those systems that have a soft real-time time constraints. And Throughput is good for small heaps or a very short-lived applications. And you can see here, Throughput has the highest throughput because it doesn't have write barriers and doesn't have read barriers. But in the other hand, it has the longer pauses. On the other hand, you have GenCon CS, which have the fewer pauses, but because of read and write barriers, there's a penalty on throughput. So there's always a trade-off here. So this is a comparison between the most common GCs out there. So on the yellow blocks there, they are the most common GCs. So I went with you today. GenCon is very similar to CMS, which is CMS from Hotspot. Balance very similar to G1 GC. Both are generational, both are region-based, right? And on the blue side there, we have the puzzleless GCs. The lines there are a little bit thinner because they share a little bit some trends there, but they're not really similar to each other. For instance, ZGC, Shenandoah, they are both region-based. Metronome is region-based. ZGC, for instance, uses that multi-mapping that I talked to you about with colored pointers, right? Shenandoah has two versions. Version 1 uses Brooks pointer, and Shenandoah version 2 uses a similar barrier to GenCon CS, right? So they use different techniques to move objects concurrently with the application. And in the bottom there we have Azul C4, which you require special hardware or software to run that GC. So in summary, if there's something that I want you to get out of this talk is that there's no perfect GC that fits all. And if you don't care about pauses at all, you should go with the perfect stop-the-road GC. For instance, of throughput, right? It's going to have the higher throughput, but the longer pauses. On the other hand, if you care about pauses, you should go with the perfect pauseless GC, right? It's going to have the shorter pauses, but it's going to have lower throughput because of the read and write areas. So each of these policies is going to deal with heap fragmentation differently. There's no perfect GC that fits all. And because of read and write barriers, this pauseless GC is not going to have as good throughput if you didn't have them, because you need to keep track of these moving objects concurrently somehow, and read and write barriers is the way to go. So here are some links if you're curious about OpenJ9. It's a very open community. We are open to any contributors. It's a really cool project. It uses some of the frameworks of OMR. So OMR is another open source project that has components to build a runtime, and that's being used in OpenJ9. And adopt over JDK there you can use to get the builds from both Hotspot and OpenJ9 and play around with it. So that's it from me. So before I finish off here, I promised that I was going to show you this book. If you want to know everything about GC, that's the GC Bible. Everything you want to know, you can find it there. And just a few seconds I want to spend on the slide here. If you want to start off like tuning in your application, you can start off with this with these different options, right? And one that I would really encourage you guys to use is Verbal GC, but this option here is related to OpenJ9, and the good thing about this is that you can get the output of Verbal GC and put into this tool GCMV, and you can visualize how the memory is behaving in your application, which is pretty cool. We constantly use internally to see how each of these policies are behaving depending on the workload. And that's all from me. So I'll jump into the Q&A, see if there's any questions there.